Namaskar and hello. Welcome to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subject by right understanding and clarity of concept. Today in our playlist class 12th Physics and Physics Made Easy, we'll discuss few more multiple choice question on electrostatics, and all these questions are very important and frequently asked in several competitive exams. Let's start. Two metal conductor pairs have radius 1 centimeter and 3 centimeter, and they have respectively minus 1 microcoulomb charge and plus 5 microcoulomb charge on 3 centimeter pair. Now by a metal connection wire they are interconnected. Now after that interconnection, what will be the final charge on larger sphere of 3 centimeter radius? We have to find out. So in metallic pairs, when we charge, all charge will remain on outer surface, and at surface and at all internal position potential will be the same, and complete metal pair will behave like an equipotential surface with surface potential K capital Q over R, where R is radius of sphere and capital Q is total charge on that sphere. Now these two sphere got different radius and different charge, so they may have difference in their potential, and when we interconnect two isolated metal pair by a metallic interconnection, the two sphere will become equipotential surface and they will circulate their charge such that potential of both spheres will become the same, and potential is a ratio of charge to radius. So after interconnection, when both sphere got same identical potential, the charge on two sphere smaller of 1 centimeter and bigger of 3 centimeter radius will have ratio of charge as per ratio of radius 1:3, and the total charge minus 1 microcoulomb and plus 5 microcoulomb when added together become plus 4 microcoulomb, and this plus 4 microcoulomb charge will divide in a ratio 1:3 in 4 parts, and one part of this is 1 microcoulomb plus charge will remain on smaller sphere of radius 1 centimeter, and the larger sphere of 3 centimeter will have 3 times more charge, that is 3 microcoulomb. Here option 2 will become a right choice. So when two metal pair are interconnected, they become equipotential, and at equipotential conditions charge will have proportionality with radius, so charge ratio become equal to radius ratio, and by that understanding we can solve such questions. Next question is related to Gauss law, which relate flux across any closed surface to charge enclosed in that surface. Now here we have given a hollow cylindrical closed surface with a small q charge just at its center line symmetrically placed in this cylindrical volume. Now the total amount of flux across this cylindrical plane denoted by B in this figure is phi in voltmeter unit. Then what is the amount of flux across flat surface of circular shape A? We have to find out. So we know if this cylindrical surface enclosed q charge, then total amount of flux from this entire closed surface is q upon epsilon, and since out of this total q upon epsilon flux, psi flux is coming out from B cylindrical portion, so the remaining flux is q upon epsilon minus psi, and since this charge got symmetrical position with respect to surface A and surface C, so the total remaining flux q upon epsilon minus phi equally divide from A and C. So flat A surface will have half of q upon epsilon minus phi flux as denoted by this option 3 here. A square surface of side L meter by L meter and an uniform electric field intensity of E volt per meter intensity both exist in this paper plane as shown here. Now electric field intensity direction makes an angle theta with this horizontal side of square surface. We have to find out total amount of electric flux across this square plane. So we know flux phi in an electric field intensity E from an area A is a dot product of electric field intensity vector and area vector, and this dot product is equal to magnitude of electric field intensity, magnitude of surface area, and cosine of angle between E vector and area vector. Now area vector is directed normal to the surface, so here area vector is normal to the paper plane and E intensity vector is along paper plane, so area vector and E vector got 90 degree angle and cos 90 intensity is 0. So in this case, when electric force lines are parallel to surface plane, the total amount of flux across such surface whatsoever their area or orientation will become 0. So here option 4 is the right option for this condition. Suppose this electric field is normal to paper plane, then E vector and area vector will have 0 angle and cos 0 become 1, and maximum amount of flux will pass through this area, and area vector is L square, electric field intensity is E. So total amount of flux will become EL square, option 1. Similarly, electric field intensity vector shown by black lines and arrow directions is not along this square plane, but the two plane got certain orientation, and normal to area vector and E vector if got theta angle, then dot product of electric field intensity and area vector, total amount of flux across this surface will become EA cos theta, and in that case our answer will become E, and area is L square, and angle between area vector normal to the plane and E vector is theta. So the flux is EL square cos theta, second option. Next two examples are identical in nature but very important from examination point of view, as they are very frequently asked in present days examinations. And in these questions, in space distribution, electric potential is given in space coordinates, as here electric potential in xyz coordinate is 6xy minus y plus 2yz. If xyz is in meter, then potential is in volts unit, and we have to determine strength of electric field or amount of force on any charge at a certain specified ordinate, and given point here is 110 ordinate, where we have to find out strength of electric field. We know that in an electric field, potential difference will occur when displacement is made along the direction of electric field, and product of electric field intensity and displacement opposite to the direction of electric field become positive potential difference. So if electric field is only in x direction, then displacement along x direction will produce potential difference, but displacement along y direction or z direction in x directed electric field makes an angle 90 degree and won't involve potential difference. So potential difference by x component of electric field depends only on x displacement. Similarly, electric field of y direction produce potential difference by y displacement, and z component of electric field will produce potential difference when displacement is in z direction. So if displacement is only in x direction, and if we make partial derivation of potential with respect to x displacement, then negation of that become electric field of x direction, and as potential is 6xy minus y plus 2yz, and when this is differentiated with respect to x, keeping y and z constant, 6y being constant will bring out, and x got differentiation with x1. So this first term become minus 6y with this negative sign, and y and z both are constant, so constant partial derivative becomes 0, and for this given coordinate y is 1, so electric field x component is minus 6 eta. So there could be first or 3 may be a right choice, and that depend upon y and z component of electric field. Similarly, y component is obtained by partial derivative of potential with respect to y displacement with a negative sign, and for this differentiation with respect to y of this potential we'll keep x and z constant. So first term will become 6x, second become minus 1, and third become 2z, and z coordinate of observation position is 0, so this term becomes 0, x is 1, so this is 6 minus 1 with this negative sign minus 5j. Similarly, when potential is partially derived with respect to z displacement, keeping x and y constant, this become 2y, and with observation point coordinate y equal to 1, this is minus 2k. So my electric field is 6 eta minus 5j minus 2k. This first option become a right choice. In space, electric potential in terms of xyz coordinate is defined as 6x minus 8xy minus 8y plus 6yz. If xyz are in meters, then potential is in volt unit. Now we have to find out amount of force on 2 coulomb charge which is placed at coordinate 111. So we know potential difference by x component of electric field is contributed only when displacement is in x direction. Similarly, y component of electric field contribute potential difference with respect to y displacement, and z component of electric field contribute potential difference only when displacement is along z direction. So total potential difference by 3 component of electric field is given by this mathematical expression, and if we make partial derivative of potential with respect to x keeping y and z constant, then electric field x component is given by this mathematical relation. And here when this potential function with y and z constant is differentiated with respect to x, then first 6x will give differentiation 6, minus 8xy will give minus 8y. There is no x component in minus 8y and 6yz, so its differentiation becomes 0. Now for coordinate 1 1 1, when y is placed as 1, this figure will become minus 2 with this minus sign, this become 2 eta. So x component of electric field is plus 2 eta. Similarly, y component is obtained by this partial derivation. When this potential function is differentiated with respect to y keeping x and z constant, this first term is 0, second term got minus 8x, third term got minus 8, and this third term got plus 6z. And for 1 1 1 coordinate, x is 1, z is 1, and this calculation will become plus 10j. So y component is plus 10j volt per meter. Similarly, z component of electric field is obtained by differentiating potential with respect to only z keeping x and y constant. So first term got 0 differentiation, second also got 0, third also got 0, as there is no z in these 3 terms. But this last term will result as 6y, and at given 1 1 1 coordinate, y is plus 1, so this become minus 6k. So electric field z component is minus 6k. Now this electric field magnitude can be obtained as ex square, ey square, ez square square rooted, and it comes as 2 root 35 volt per meter, and on 2 coulomb charge, amount of force QE become 4 root 35 Newton. So similar type of questions can be solved if asked in any exam. A solid conductor sphere is charged. We have to comment on its potential. So all charge will reside only on outer surface, and in spherical body, charge will uniformly distributed with identical surface charge density over entire outer surface. Now there is no internal source charge or internal electric field. So there is no potential difference in this volume whether this conductor is solid or hollow. So conductor sphere when charged behave like an equipotential surface, and potential on its surface is kq by r or q upon 4 pi epsilon r, and this potential will remain the same over entire internal volume. So option 1 is right choice, and the maximum potential is at its surface, and the surface value and everywhere in this entire volume potential is the same. But outside the spherical surface, this spherical charge act like a point charge acting from center, and if observation point got a distance smaller from center, then potential is inverse function of that distance, and inverse rectangle hyperbola relation of voltage and distance from center as denoted by this mathematical relation will result. If someone has asked electric field intensity of this charge sphere, then intensity is maximum at surface and it is kq by r square, and internal electric field in a conductor sphere whether it is solid or hollow becomes 0. This is again a very common examination question pattern where a charged particle of certain mass is accelerated in electric potential difference, and we have to relate accelerating potential and velocity gained by that particle. Here in this we have given a particle of mass 20 gram and charge 2 microcoulomb. We have to find out required accelerating potential so such that this particle from rest attain a velocity of 10 meter per second. So we know a q charge when accelerated in delta v potential difference will have this much amount of work done by electric field, and that work get converted into gain in kinetic energy, and a particle of mass small m with velocity small v will have kinetic energy half mv square. So here charge particle got 2 microcoulomb charge. We have to find out accelerating potential. For this 20 gram mass, it must be converted into kilogram. So gram is converted into kilogram, and velocity is 10 square 100. So this 100 and 1000 10 to the power minus 3 get cancel out. This 2 and this denominator 2 is also get cancel out. So this figure is 1. So potential difference is 10 to the power minus 6 to second side become plus 6 divided by this 2 when side is changed comes in denominator. and our figure will be 500 kilovolt in this question. Similar type of question can be asked for electron, where in place of charge we will put electronic charge E, and in this expression E and M got a ratio, and that E by M is called specific charge, and for electron it is highest 1.76 into 10 to the power 11. So if one know E by M ratio of electron, such questions of electron motion in electric field can also be solved easily. We have given two source point charges plus small q and minus small q at position A and B, which are at 2L distance from each other. Now there is a third test charge capital Q placed just on mid of joining line at position C, and this test charge, if moved over this semicircle trajectory to position D to other side of minus Q, we have to find out total amount of work done in movement of capital Q charge. So when this capital Q charge is moved in this trajectory, its distance with respect to minus Q charge in the beginning and in the end would be the same. So there won't be any potential difference contribution in minus Q field when this capital Q charge is moved. So amount of work done in zero potential difference condition would become 0. But in plus Q electric field, initially capital Q is placed at L distance. So initial potential of small q at L distance is kq by L, and finally it become 3L distance. So potential at D point from this small q charge at position A become kq by 3L. So this potential difference is a negative potential difference minus 2 by 3 K small q by L, and in this potential difference when capital Q is moved, the amount of work done will become negative 2 by 3 K capital Q small q by L. This option 3 become right choice. In an uniform electric field of E volt per meter as shown by these black lines, we have three observation position A, B and C, and we have to find out relation between electric potential of these 3 points. So in such uniform electric field, if displacement of charged particle is perpendicular to electric field, there won't be any work involved in this movement, so there won't be any potential difference, and such lines which are perpendicular to electric field lines become equipotential lines. And along electric field, when positive charge is moved, work is done by electric field itself and there is negative change in potential. So electric field is directed from high potential to low potential. So here this B position is farthest in opposite direction of electric field, got maximum potential, and this position A among A, B, C got least potential, and electric field is directed from high potential to low potential. So here option second, electric potential is maximum at this B position, is the right choice. We end this learning video with a lengthy and difficult question, but conceptually it is a very sound question. We have given three concentric pair of radius, small a, small b and small c, and we call these pair as capital A, capital B and capital C, where radius A is least and radius C is highest. Now they have surface charge density respectively plus sigma coulomb per meter square, minus sigma and plus sigma coulomb per meter respectively. Now the potential on surface of first pair A, second pair B and third pair C is respectively VA, VB and VC. Then if potential of A pair surface and C pair surface if is equal, then we have to find out correct relation among three radiuses A, B and C. So we know to find out potential at any observation position, we can use superposition principle. For surface of sphere A, potential contribution is potential of sphere A, sphere B and sphere C, and we know outer sphere for internal position contribute same amount of potential as on their surface. So at A position, surface charge density sigma multiplied by 4 pi A square is total amount of charge, and 1 upon 4 pi epsilon Q upon A would become potential at surface of sphere A, and it is in terms of surface charge density and radius is sigma A square upon epsilon A. For this B sphere having negative sigma surface charge density and B square product will contribute its total amount of charge on sphere B, and at its surface with radius B, potential is sigma B square upon epsilon B, and the potential on sphere B surface and this internal position by this charge is the same. So this is electric potential contribution at position capital A by sphere of B radius. Similarly, this is potential contribution of C sphere, and when sigma upon epsilon brought out as constant, it is A minus B plus C. Similarly, for potential at this C position, this internal pair act as a point charge acting from center, and at C distance from center, electric potential is this B sphere with negative surface charge density at C distance contribute this potential, and C sphere got C radius and C distance from center on its surface contribute this potential. And when sigma upon epsilon is brought as common, this is A square minus B square divided by C plus C. And if potential of A and potential of C sphere is same, then these two figures are same. The C is common, get cancel out. So A minus B become equal to A square minus B square by C. A square minus B square can be simplified as A minus B product A plus B, and when we simplify things, A minus B will get cancel out and A plus B become equal to C. So this first option become our right choice. Students, we have prepared 6 learning videos on MCQ on electrostatics and tried to cover almost all examination question pattern and conceptual understanding considerations. And with these 6 learning videos, you will surely receive great comfort in any competitive exams. The link of all these videos are given here in description and you can get advantages of that. We end here with a special note of thank for viewing and appreciation of our videos. Thank you very much.